So, welcome everyone to this presentation of dynamic analysis of floating bridges. We will record this session, and everyone who will not, who are participating, will not be shown in the recording unless you ask questions at the end, and it is a possibility to do so. It is Mitja Papinutti who is presenting, so the floor is yours, Mitja.
Thank you very much, Kersti, and thank you for this opportunity. This is one of my second presentations about the research I did. And the first part was already presented a while ago, and you can find it if you either search through the website of the Statens vegvesen, or you can just type into YouTube my name, Mitja Papinutti, and Statens vegvesen. You can find hopefully these two video presentations uploaded. And before I started, I would just like to mention two important contributors. This is Statens vegvesen, who is supporting this research, and of course NTNU, where I did prefer much of the work that I present here today. And here on the down right side, you can find my contact address. And yes, we can start with the presentation, which starts with the story of E39 and building the highway across the fjords, which are deep and wide. And because of that, the new technologies and new concepts have been developed over the years. And now a few concepts has been really pushed forward, and you can see those solutions on the pictures here. One of the solutions is a multi-pontoon floating bridge. And they are both in different sizes and varieties. One of them is a multi-span suspension bridge, and one of them has this multi-pontoon curvature. All of them very nice aesthetic solutions. And then also you have floating tunnels, which they are also a suitable technology to cross those fjords. And this is where my research was mainly focused into those floating structures and how to make an efficient design. And for an efficient design, you need good numerical tools that they can accurately and representatively present all the environmental loads and how your structure is going to behave. And before starting with, let's say, science, let's have first a global view on the things that are given us by Mother Nature. And these are, let's say, extreme wind events. They are happening often and often since the energy in the air seems to be increasing. The amount of energy released is through extreme events. And this is on the left top picture. You can see the category of typhoons when they pass their hurricanes on the Asian side. And you see that there are quite a big area across the globe where these extreme events happens. There are also other parts which are also maybe locally known to have very high winds. So we want to be sure that our structure will be able to resist those high wind events. And if it happens that you're one of the countries near this red color area, then you really want to have a safe wind design. And also another phenomena is our earthquakes, and these are due to tectonic movements of the plates. And we see there are quite a lot of areas around the world. And if it happens that you build a bridge across one of those points, then you have to consider this into your design of the bridge. And since we'll be talking about floating bridges, we have to respect to the wave energy. We also like to know how much waves or how high the waves are in a respective area where you're building it. So it seems that there is a lot of energy area in the oceans and a little bit less energy in the smaller seas. And our bridge today will be placed in Norway. This is at the middle of the top picture. You see that there we have some waves. We have possibility of strong winds, but we have less earthquakes today. Yes, so and before we start with the presentation, I would like to do a small experiment with this presentation. I would like to have it more general view on this matter, and I would like to that you pick up a vehicle. I would like to sit in one of those vehicles, and during presentation, it will help you keep in track So we have here 4 main groups. The first group will be somebody who thinks like a researcher, who is really interested into mathematics and performing new things and so on. So this will be, if you find yourself being that person, then if you see a blue color and the scar, that means this is a slide for you. And then we have an engineer, somebody who is designing, who's actually working and making adjustments and planning, and so thinking how it's the best to be done. Then you are in the car of yellow. And then we also have somebody who is an owner of the bridge, who will have to eventually pay and also maintain the bridge over the years to come. And there's also an independent group of people who will be just using the bridge and driving through it. And maybe it will be your holiday that you're just as a tourist driving through this bridge. And what is interesting about these groups, they'll be all using the same bridge, but you might have a different perspective on this presentation. Yes, so let's start with that thought. And I have to start with essential part of my research, which was actually investigation of the bridge dynamics. And to do so, we put there some equations which we have to solve and which help us to understand the structures better. And this is something, what you see on the right top side, very interesting for researchers and engineers, but perhaps a little bit less interesting for other groups. And essentially how we are able to solve this complicated behavior. Because now that we have bridges on the sea, we are exposing them to a lot of new environmental loads, such as wind and waves. They are particularly playing an important role in design, since they are a main contributor for dynamic excitation. And particularly in my research, it will be focusing today on how to improve, for instance, the wind damping and wind stiffness formulation. As you will see, there are a variety of possibilities how we are able to simulate those effects. And my research particularly proposes to improve these 2 parts in order to get more representative solutions. And moving forward, I would also like to introduce a new, let's say, a concept, a new angle of view, how to look at the research or the results of the research. And the first is the concept of reliability, and that might be fairly known to researchers that work in this area. But it's also particularly very interesting for the owners, since the units of this graph below, you can see you can have 2 units. One is the lateral wind response, which is meters. And this is quite convenient for the design, or you can simply translate it into some euros format. Let's say that could be billions in euros, and that could be potentially interesting for the investors. So what we are trying to achieve through that parameter is reliability. Actually means how close we are to the actual solution. And that means 2 things, reliability and valid results. We would like to have both on the target. So the idea is that with increased precision, we achieve more reliable and more valid results. And this is also a graph showing here below. We'll see here a multi-phase evolution of this equation, what you see up there. This has been, many groups have been involved in this work and have been done over the years. I've been privileged to work with one of those groups, and we added slowly iteration per iteration, we added different effects, which started with hydrodynamics, which gradually increase the accuracy of our floating bridge simulations by simply mimicking the mass and the damping. And then we also add the currents, which have a little bit smaller contribution, but we also decrease we increase the reliability of those solutions when we have included them. So we are more certain that our models are correct. And then we also implemented some wind in time domain, and we found a more, let's say, cheaper solution for those responses, but also more reliable, which is the end goal. And today, what I would like to do is I would like to put us a little bit more to the right side, so to have perhaps a little bit more accurate solution, but especially more reliable solution, because those proposals, those models I'm proposing, are in line with the wind tunnel testing. So that's so that will be the argument what we're trying to achieve here today. And starting with the focus, at the moment we have used so-called quasi-steady-static formulation of the aerodynamic wind damping and wind stiffness. So that might be interesting for a researcher and engineer, and this is an important model that has been used widely in design across different solutions. And those models have been found as good enough, and particularly they are very attractive for designers because they have accessible results. That means that results can be simply obtained by CFD analysis. We can run some simulations, get those coefficients, and just insert them into this matrix, and then we have those values available. And this is good. That's also good because it's quite straightforward to implement in some numerical software, and that's why it has been very popular. The disadvantage, of course, is that, as you can see in these matrices, there are a lot of zeros there. That means that those terms will not participate anything. And this is particularly a problem because this is analytical solution. This is based on the theory of putting a few vectors together, but it's not really reflecting the wind tunnel results. And what is reflecting actually the wind tunnel results is more or less a very good attempt to linearize the flutter coefficients. And this is also being a widely used method in the research area. It's also, of course, used in the design, but in design it's rather used as a final check or final investigation that our bridge is stable, rather to use them actually to calculate the, let's say, wind buffeting forces or the forces that are directly related to the damping of the structure. So our idea is that those models are better than the quasi-static because they provide more accurate results of coupling effects. You see here that the matrices are full, there are no zeros, and all the values here are wind tunnel measures. So that means that we are having the forces which are corresponding to the wind tunnel measurements, which the quasi-static does not necessarily have. And that also means that using those self-excited formulation, we will have a good reliability and consequently good match with wind tunnel results. And now you can perhaps ask a good question, why they are really better? Can you prove that they are better? And yes, we can perhaps show some results. And one of the colleagues that did in NTNU is they did a series of experiments for the aerodynamic cross-sectional Hardanger bridge, and they have a very nice testing ring in the NTNU wind tunnel testing facility, where you can simply extract for each individual frequency. You can measure the damping and the stiffness of each part, and each dot here on the graph presents one measurement. Both damping and stiffness are now in the same graph, so you see that here, for example, you have the red ones or the damping, and the blue ones or the stiffness terms. You see that also some data is scattered, some data is less scattered. Essentially what we do with those models, if we would like to use them in time domain models, we have to make continuous functions. And there are two ways of doing that. One is we fit a predefined functions, for this instance rational functions, to it. Or another possibility that has been explored in this PhD, you can simply fit in the polynomials. Now you'll see the rational functions expression in presentation, and you also see the polynomials. What is perhaps important here to say is that the polynomials have usually never been used in time domain simulations up till now, because the theory simply was not suited for it. And what we explore through research is a new way of formulating the self-excited forces, and we are now allowing actually to use the polynomials as well, because we're taking a more general approach. So that will be, of course, a big benefit to have this simple way of fitting of the data. And these are actually measurements performed in the wind tunnel. Yes. So this is how do we get, and this is one of the tests, and that has been also conducted. Based on the data we have up there, we can fit our numerical models. And in this case, we have 3 numerical models. One is rational functions, one is average flutter, and one is quasi-steady state model. And you here on the left side, you will see 3 forces. And first column, you will also see 90 seconds of realization that has been tested in the wind tunnel tests. And this is really tough tests for the self-excited forces, because we are testing a spectrum of frequencies. So it's not only one frequency that is tested. It's not only one that has been used for getting the flutter derivatives, but we're actually testing across the entire spectrum at once. So that means we have a lot of frequency here, and we are now testing the performance of different numerical models and how they match. And you see here in the red color, you see the experimental results, and then you see in black color the rational functions, and the green average, and quasi-steady static is the model we are comparing here. And on the right hand side, you see the zoomed interval that zooms a little bit in, because it's a lot of things happening there. And you see that the red color is our reference. And for both moment and lift forces, the rational functions are following it quite well. They're not exactly following it, because this is really, it's a tough test, but they're following it quite well. But also, you see for the drag, none of the methods have really followed well the experiments, and this is due to the fact that the drag force exhibits nonlinear behavior, and it's multi-harmonically excited, so we don't really expect to follow it, because our models will not work there anyway. But we do expect to have a lift and moment, which are also very important for design, to have and follow it good. You see that the quasi-steady state is following a little bit out of the line here, and the rational functions are following it quite well. For lift, there are small differences, but we also tested not only one event, we tested totally 15 wind events. That means we can take an average of all these events, and we have a very good agreement for the moment and lift. That means that the rational functions are actually being very accurate in that sense, and they are really representing the wind tunnel experiments. So that's why we think those models are better compared to quasi-static. And also, there is an alternative way. What we can do, we can simply transform this signal, these forces, with the Fourier transformation. And on the right side, you will now see a spectra for which we tested our tests from the 0.25 Hertz up to 2.5 Hertz. We tested this for different models, and you'll see that red is again the reference of the measurements. This is where we want to be with our models. And then we have rational functions that are quite well following it. And for the lift, we have small discrepancies in the higher frequency range. And for the drag, of course, all the methods are off, since this is some other phenomena, and our models are not suitable to simulate that. But most importantly, the moment and the lift, they are following it quite well. And the quasi-steady state functions are being either they overreact or they underreact in case of the lift. They are simply producing different forces. And this is mainly the reason because they are derived from from theoretical perspective, and they're not based on the actual measurements as the flutter derivatives are. And you might say this is perhaps conservative, more conservative, less conservative. Essentially, it's not really important how do you think in this perspective, but it's simply not a suitable model to represent the actual damping. So having more damping on the structure is actually dangerous because you're under-designing your bridge. Having more damping on the structure is also not cheap to build a bridge. So it's good to have representative models. And definitely these flutter derivatives, they present one of a very good inaccuracy. So first we have let's say an overview that's already present in the previous presentation, and that might be interesting for some researchers, engineers, and of course also the owners, that we have it really good in GRIF. Pretty much the bridge response, the wave loadings, and the wind. The wind itself, it's consists of two components. One is the wind buffeting load itself, how to simulate the turbulence. And I think over the past years this has been also improved. We can now have non-homogeneous wind fields, and we can simulate very, let's say, realistic design scenarios. Where I still see in design that it is quite popular to use the quasi-steady static interaction, which is supposed to be fine, but we are proposing here to replace this with the flutter derivatives. So the question is now how to achieve this. And the goals of this research were that we will build on existing know-how and we'll try to contribute to this new formulation. In order to do that, we have to build on existing way of doing things. So we cannot just implement a new model into our small code. It has to be part of the whole solution, so to say. So everything that has been done up till now has to remain because it's a good solution, but we'd just like to do a small improvement. And this was achieved by inserting this into new mark formulation. So the main goal here was to be simple also for engineering practice. And before I continue, I would like to have a small example here. And these are two bridges. One is TLP, which stands for Tension Leg Platform Suspension Bridge. It is like a regular multi-suspension bridge. Instead of the middle pylons are founded on the floating foundation, which is anchored to the sea bottom. And on the right-hand side, you have this multi-pontoon cable stay bridge. And what I would like to compare here, it's perhaps interesting that see how different environmental loads may have a different effect on the bridge design. And definitely for TLP suspension bridge, the wind is really dominant force. So there is a lot of wind catching in this area of the deck and tries to force to move around. And where there is only a few points that actually bridge interacts with the water. And so that's more perceptive to the wind, which is good for our research. I guess this is the place where we really like to use it. On the other hand, you also have a multi-pontoon cable stay bridge where it's perhaps a little bit less perceptive to the wind because the deck is a little bit lower, closer to the water, where the wind is not that turbulent and the wind profile is much lower. And also the bridge itself has enough stiffness to not have any large excitation of the forces during the wind, but is more perceptible to the waves because we have a lot of interaction points with the sea through across this curved bridge on the right side. So in both cases, it is been found that it is very important that we consider all sorts of the damping. So all the damping is welcome because that helps lower the negate and somehow lower the total response of the bridge. And that's why we think that those improvements in accuracy will be beneficial for both projects. And of course, moving forward, the question is how do we do it? And now we are just left with one group, and probably this is something very interesting for researchers. And this is something that is known as a rational function that has been fitted to the flutter derivatives and has been famous, but sadly for it, it's been only used in the research. We don't really see it much in action when you actually design a bridge, and perhaps we'll see some of the reason why is this so. So the first one, this is simply at the top you see an expression which is directly fitted to the flutter derivatives. So there is a fitting procedure that you have to apply, and it's called nonlinear regression fitting because there are terms there that needs to be fitted both to elastic damping and elastic stiffness at the same time. Plus it has this nonlinear property, so you need to have a good fitting procedure that you're able to even fit the function. And once you fit it, there is the good thing about these functions is they somehow do all the checks box for causal dynamic system theory, and you already have a fully developed expression which you can directly implement in the software, which is down there below the equation. So if you're able to fit the data, you can directly use this model into your in your bridge, and you'll be able to simulate the self-guided forces. Right. But it seems that software implementation isn't that straightforward. The software that have been applied in recent years or mainly commercial softwares, and most of them, they don't have access. You don't have access to code your own code. And this is a big disadvantage of this rational functions, which would be actually a perfect candidate for that. But simply you cannot put in the software and try to simulate your behavior or bridge response. And this is particularly also a difficulty in using of time domain models in our analysis. The other third point is that validation of the methods, it also is important part of the, let's say, implementation. You need to have some references based on which you're able to validate if your method is correct or not. And since these are not quite straightforward expressions, it's sometimes hard to say what's right and what's wrong. So these are a few difficulties. I think they are the reason why this hasn't been already used and applied in the general design of every bridge. So there are, of course, this is how mathematically looks, but there are some good solutions we found during this research, and hopefully this will now be we'll be able to target a larger group of people working in this area, and this is especially targeting engineers, and we would like to also make owners aware that this theory now exists and that we are approaching to the point where we are able to use this in our everyday design, not just some separate check, but actually to have good design values. So what you see here on the top are two equations. One is the equation of the hydrodynamic linear wave radiation forces, and below down is our elastic approach. And this is how we are trying to mimic the rational functions or any other fit that we perform to the flutter derivatives. And what you'll see for both of these two equations, they are exactly the same. So mathematics is exactly the same. The only difference is the input. So this aerodynamic damping or hydrodynamic damping are two different inputs. So in essence, if we are able to prepare the aerodynamic damping table, we insert it and we are able to simulate the aeroelastic forces. So what we have to do in order to get to those equations is pretty much rewrite the whole theory and make it in the format that is now suitable. But the good thing for you is you don't have to do that. You don't have to go through the whole theory. You can just simply use the same functionality and apply the aerodynamic damping, and you'll be able to mimic those forces. So with this approach now, it is available for different softwares, meaning that hydrodynamic approach is quite popular out there, and there are a lot of commercial packages that already have this functionality. So if they already have it, we can also use those softwares to simulate the flutter derivatives. So that's handy thing, because this is our way into different softwares. And we now have prepared and validated all the theory. This will be published in my PhD and also have been published in the article. This is something that has been done, plus the theory provides validation references. When you implement it, you're actually able to test and to see if your implementation works. And that's a big benefit of this research. Both of all the three concepts are now being introduced. So we have here some very good news for researchers and engineers. And the first one is we found, beside everything I present today, we found an interesting interrelation between real imaginary part of the transfer function. What does that mean? Scientifically, it means that we have found that we don't really need to use the parametric modeling anymore. We can use simple non-parametric modeling. That means the rational functions are parametric because they fit to both stiffness and the damping at the same time. But we can now also use the polynomials fitted independently to both damping and stiffness. And this is a big advantage because polynomials are simple to use. Everybody can use polynomials. You don't need to have any special equipment or software. You can do it in Excel. You just need to introduce the right damping table to our method. And this simplifies a lot since we avoid all the nonlinear regression fitting and also all the difficulties with the convolution. So technically you can do now with our approach, which is numerical, which works on the numerical transformation, you can put in any type of the curve, numerical curve you like. There are just a few basic rules you have to obey. And this is what we would like to educate through our research, how to simply do that and use the equation. And this is now, of course, an integrated part of our dynamic analysis of floating bridges, that we are now actually able, in a very simplified, as much as possible, simplified way, we are able to simulate this flutter derivatives. We have developed the method that introduced those equations into dynamic equations, and we have also simplified a polynomial approach, which has been approved and published. So, of course, here's the big question: what is next now? And this is, of course, the point where you run out of all the funds of your research. And let's say we'll try to move this into some more practical domain. And we think that the research has been done now, and it's on a great scientific level, but it needs more work. We need to start implementing those methods into various models. And these are just a few that have been used throughout the years for the floating analysis. And a lot of them have this possibility to be able to simulate those effects. And we would now like to apply those models, and we would like to now educate, and we would like now engineers to use it, and we would like to make it also aware the owners that those methods should be part of their design. So when they trust design to, let's say, a group of companies, they should expect that something like that is partially considered in their design. So in overall, we would like to improve the current way of doing things. And I believe through that research that we did, it's quite a good chance that we are able to successfully introduce those methods in pretty much all the softwares. And this was also a slide from my previous section, is that we have this is just a section of a few softwares that have been used. In my research, I particularly investigated one. I'll put it anonymously now, and we found that these effects can be simply, the flutter derivatives in time domain can be simulated in the time domain simulations successfully, and this software is used for the bridge design, and it's not any special hydrodynamic software, and you don't need to have any special access to the code. You can just reuse the existing functionality of hydrodynamic linear wave radiation and simply introduce the right damping tables. And we will now like to introduce those methods also to other softwares that has been used a lot throughout the design, and here are a few examples on this slide. And so in conclusion, the research has provided all the, let's say, specification of dynamic loading on the floating bridges. Throughout the PhD, it looks like a guideline where all the effects are listed and described after each other. We are just adding the terms, as you saw in the dynamic equation, and then we come to the point where we'd like to improve the wind formulation with the self-excited formulation, and we did that by introducing a new equation that we can use. We also simplified the theory with simple polynomial fits to flutter derivatives. I think everybody will like to work with that theory much more than with nonlinear regressions. And we have a good efficiency of those algorithms. We think they are efficient enough to be introduced on something large scale projects like 5 kilometers long bridges or 10 kilometers or whatever you might build. And of course, it increases reliability, and we are more accurate on the results. That means, of course, directly more accurate ultimate limit states and serviceability limit states, which also means a big money saving. And that will be for today's presentation everything. And I would like to thank you for staying with me. And I would like to open for some possible questions. Thank you.
Thank you, Mitja. And then it is possible to ask questions, either if you have something in writing or if you would like to do it orally. So please just unmute and ask questions. That was very, very quiet today.
That's very shy, yes.
Yeah. Maybe I can ask a question.
Please start.
Yeah.
Yes. Thank you.
Because I see that you are you have proposed that this method, this wind self-excited forces, to be simulated in the time domain in the same way as that you do in the hydrodynamics, right?
Yes.
Because I'm not have that deep knowledge about the wind, but usually why we use this method in the hydrodynamics is because the damping at both ends, low frequency and high frequency ends, are zero. That makes numerically feasible. Is it the same for the wind part? Self-excited lows at high and low frequencies, you get zero.
Yes,
damping.
that's actually a very good question. Thank you for asking that. I'm gonna roll a little bit back now to one of the equations which I showed. Let me just find the right one. This one. Yes, so you were asking here that in case of the hydrodynamic approach, you have damping, which starts with 0, goes to some value, and then goes down to 0.
Yeah.
That means that those transformations are possible, because here we have infinite integrals, and you need to have this format in order to be able to simulate this effect. This is a requirement of the equation.
Yeah.
And in the same elasticity, we use the same mathematics, but this damping is different. Now, as you might see here on the left side, I haven't wrote all equations. This is now the total solutions. This is just solution for the frequency dependent part. So in hydrodynamic, you're simulating the frequency dependent part, and our elasticity also, we are just using here the frequency dependent part. The one that is not frequency dependent, because we also have infinite contribution, we can solve it analytically by simply adding a matrix term into Newmark. So there are more to this equation, which are called infinite contributions. And how do we get? We simply subtract transfer function for an infinite. So we get a damping table that starts from the 0 or starts from something and then goes down to the 0. But this is only one part of the elastic vector. The difference between those methods actually is that we have more infinite contributions for the elastic vectors, and we simply solve them quite straightforward analytically. And that's a good point. This is exactly the difference. But at the same time, the frequency-dependent part is resolved exactly the same. So there is a little bit more added to these equations, but since they are more straightforward, I haven't really, I simplified it here for this presentation. But that is a good point. Thank you.
Yeah, thank you.
Do we have another question? I think I saw someone unmute a minute ago. No? Okay.
I have a small question here. What about the variation of the load on the bridge?
All right.
It will be used by cars, by trucks, by a lot of the variation of the load. Is it part of this study or not?
Okay, so you're asking if the variation of the load when it's exposed to different traffic situations and so on, if it's considered in this study. So I can maybe roll back to the slide where we did some investigation in the wind tunnel tests, and this is perhaps this picture. So this data has been extracted for the wind tunnel results. Based on the cross-section you see here. So there is no traffic there. There's only rails and guideways and everything that belongs. And again, this is not part of the floating bridge project. This is some other very similar cross-section. But for the future, this might be possible, of course, to add there some traffic. What you end up is a different set of data, but you can use the same mathematical procedures to apply this to to a bridge design. So the focus of this research was not so much the data, it's more the mathematical procedures. Once you have these mathematical procedures intact and implemented, you can pretty much simulate wind tones, different scenarios of traffic and different events. Yes.
Yes. Sorry, in the middle there I muted a little bit because we had an echo sound. Were you happy with that answer, Afaf?
Yes, thank you.
Yes, thank you.
It's important to take this in consideration. Thank you for your answer.
Yes, thank you.
Okay, it is still possible to ask one more question. No? Then I think, Mitja, I will just thank you very much. Very good of you, and I'm really sorry that I hadn't sent out the information earlier. But thank you for a great presentation, and I will also remind everyone that there will be a new presentation next week. The information about that will come out later this evening. So thank you very much, and what you now have been hearing will be online later today.